Oh my God, this is my every single video is 25 minutes long. This is my fifth, sixth attempt. Hopefully, I'll do better this thing. Uh, so this is the FEA sort of solver for two problems. One is a cantilevered beam, fixed at one end, and subject to is parabolic tip shear on the other. And the other one is a plate with a hole, Kirsch solution. Um, Starting with the cantilever beam and going without going into details and trying to save time. I want to talk about some of the things that we want to be careful of. First of all, we want to load it. Uh, so it's within the linear elastic regime, basically meaning that basically meaning that our applied stress, our Young's modulus, so E being the Young's modulus to applied stress ratio should be less than 0.1. Like that's like a standard way of doing it. I've been doing that way in linear elastic regime, and we are. Um, Yeah, plane stress or plane strain or drop down we can choose, but we're gonna keep it plane stress. Um, the ratio of the height to the length also becomes a huge factor. Um, when especially when we're trying to solve for shear. But I'm just gonna hit solve and show you some of the results that it's worked. First of all, the first thing is that it's working, which is fantastic, right? FEA results on the deflection. Um, Underestimate the value. They always do. Um, this is due to shear locking, and also has to do with the fact that we have again this ratio plays a big part in that too. Um, by adding more elements here, we can make it uh sort of behave much better in shear and in deflection, I believe. And so yeah, but by far elements in X increasing the elements in X makes the biggest difference. And now the solutions are much closer to the Timoshenko and Euler Bernoulli, which are the theoretical solutions that we're trying to benchmark our FEA solution to. Um, just on the Euler Bernoulli versus Timoshenko. So Timoshenko does a really good job at capturing shear. Actually, Euler Bernoulli does not capture any shear because of an underlying assumption that all plane sections remain planar, and that's just not true, right? And where is it not true? Where the max amount of shear is being applied. Where is that being applied? At the sort of fixed nodes. So you can see where there's almost like a step change in like the shear because max shear point is basically not captured at all by Euler Bernoulli. And then shear becomes less of a factor as you move away from the fixed nodes. And so like the two solutions come together to basically be perfectly equal. Um, because shear stress over there is zero at like x equal to L. FEA solutions do a really good job. We're all following Euler Bernoulli and the Timoshenko, although they don't really do a very good job at capturing shear and um, the deflection due to shear. They do capture shear, and I'll show you in a second. Movement along the bottom X fiber, so this basically just validates what we're finding. Uh, yes, the because the beam is subjected to a parabolic tip shear upwards, the bottom node is supposed to be in tension. No, upper ones are supposed to be in compression. And as you move away from it, the away from the fixed nodes, the sort of the stress concentration decays. So these ones are the least stress and basically go to zero. Basically, there's zero stress over here on the bottom right. Sort of uh, as shown here, you know, it goes to zero stress at the very bottom nodes. And one basis as stress. So this sort of contour plot confirms what we said talked about. So the bottom nodes um, don't sort of these ones experience the peak stress over here, and then it decays as we move towards the right. Um, and then above the y is equal to 0 line. There is basically no tension. Everything is in compression rather than in tension. Um, yeah. And now the shear. So the shear, because of the relatively small number of elements in the y direction, and the ratio being like these beams are not tall and slender. We and the way we mesh them, we get this oscillating pattern, sort of like we have peak values and a small value, and then a peak value and a small value, uh, uh, sort of this zigzag pattern. So what I did to compare the Timoshenko to the FEA solution is I found the nodal averages and plotted this red line, and you can see that it captures the shear relatively well. Um, um, Obviously underestimates it a little bit, but capture like definitely captures the trend and something that we can work with. Um, Moving on to the plate with hole. Um, so just want to talk about the meshing a little bit. Y is equals to r cos theta is equals to r sine theta. Y is equals to r sine theta. X equals to r cos theta. And then I believe I already touched on it in the introduction of the video, so I'm not gonna repeat that. But what I do want to talk about is this sort of edge. These proportions are play a really huge factor in sort of how we approximate the Kirsch solution. The Kirsch solution is for a infinitely long plate subjected to a far field stress with a hole in the middle. To simulate that, essentially translating that into like geometry, what we're trying to say is that the radius of the hole should be negligible compared to the total width of the specimen, right? But that would mean to distinguish between the hole, that would mean that that our elements need our smallest element needs to be smaller than at least half as small as the radius of the hole, which means that it demands an immense computational requirement. And if we don't do that, what happens is um, we move away from the grid solution. So that's one thing. Number two, how many nodes we're able to define as that are part of the whole um, also makes a huge difference. So if we sort of just I want to show you a picture what I mean. Um, hmm. So if I have a mesh sort of like this, so I may accidentally consider this one as part of the material and this one as part of the whole. And so I will have these very sharp increases between like when I'm going from here to here, because this is part of the material and this is part of the whole. So there's going to be huge spike in sort of stress, and so that's not ideal. What we really want is like a very smooth transition from like the whole, and so the better, essentially the better we approximate this boundary, the better our solution is going to be. What I mean is that our peak stress is gonna go, our peak stress is gonna go higher and higher and higher up. And ideally, the peak stress should be over here. But because of these sort of artifacts that I'm talking about, this basically gets pulled down away from y is equal to from x equal to 0 to, like, something greater than x equal to 0. Um, and that's obviously not what the Kirsch solution says. And like it's a direct outcome of the way we measure it and how we approximate the hole. The better we approximate the hole, the better our meshing is near the hole, which is why, spiderweb meshing um is so good, and bias meshing is so good. And I have some just as I was thinking about this, I thought of it, thought to show you what I mean. This is not the exact solution, like the exact same problem, but very, very similar. Um, yes. So in this case, basically the loading is at the top, but basically you can see this looks like essentially the same problem, but it's not. It's a spherical void in an infinite solid where the stress concentration factor is 2 sigma rather than 3 sigma. Um, and so basically the loading conditions are flipped, so our equator. Oh shit, you're not. I apologize. You cannot see that. I think now you can see it. Yes, now you can see it. So, um, yeah, we want to push this as close as possible to the tip, but even commercial solvers struggle to push it like right at the tip. And so, but that's the name of the game. It goes down to how well we approximate the edge, right? Like that's a if you have a coarse mesh, then our edge looks jagged, and then if you have a fine mesh where we really need it to be, then we can approximate the whole way better. Um, yeah. Um, yeah. So this was another, like, this is what happens. This is what I'm talking about. When we are trying to, if we don't approximate the whole good, this is what it looks like essentially. And this should be 2 rather than 1, say 0.66, you know. Um, and you can see that the peak stress is not right here, it's actually right over here. And so that's the issue. Anyway, this has been the longest discussion on this. I want to move on and show you that it works. Fantastic, like it works. Look, and I want to change this to like my actual conditions, um, and solve it. And as you can see, when I set those ratios, it dampens it, but like upping the mesh density brings the solution back to convergence. Um, because it does a better job at approximating that hole. Again, we see this sort of artifact because of the hole being approximation is not great. Um, but if I push the mesh density higher, not only does my hoop stress uh, get correctly estimated to be 3, but also at the correct degrees, 90 degrees. Um, but also like this stress decay away from the hole starts improving, and then basically gets to 1, goes to 1 as you expect. And you can see that same artifact that I'm talking about. I feel like the way I did the mesh this time, it was way better compared to my previous other MATLAB solution that I just showed you. Because in the MATLAB solution, I set um, the Young's modulus inside the hole to be 0, rather than meshing the hole accurately. Here, I actually made a good attempt at meshing the hole, so this looks way better. Um, yeah, that's really all I want to talk about. That's I'll leave for the Viva, the in-person sort of call, and I want to go into refinement because I want to show you something. So this is close enough to 1. You can see that the relative error goes down. It has the right trend. I'm happy with that. But I want to talk about this more because this is the same thing again we talk about. This is so huge, and this has to do with the number of elements that we're doing and the way uh, this test is this convergence is being run in the background. So to show you what I mean, I yeah. So it runs up to 20, as you can see. It runs up to 20. Yeah, it runs up to 20. I don't think it runs up to 100. And basically these in the deployed app, these are set to be, 5, 5 and 1. So 20% of the whole width is the whole, which is not an infinite solid. Uh, it's like 80% solid, first of all, and it's not infinitely long. And so that's an issue. But to demonstrate that the solution converges much better, if we set these sort of parameters which are better representative of the Kirsch solution, and then we improve the mesh density to 100, the solution makes more sense. And but that's not running on the deployed app. That's running on the Docker app. Oh, sorry, uh, right here, on the local host, hosting it locally on the computer right now. And so you will see the difference over here. Yeah. So when we up the elements and we increase like the maintain that sort of we do a better job at approximating Kirsch's sort of conditions. Um, we get first of all, I feel like this is what I call convergence. This is almost near convergence, but not really convergence. This is I would say I'm satisfied in saying that this has now fully converged. Um, And second of all, like we do a much better job, at 10% where we get 3.13 instead of, you know, 3, which is good, but like nothing like 3.5 or 3.4 nearly what we're getting over here, which is obviously down to like the way we're approximating the solution. Anyway, last thing, and I want to show you one more thing. Like I have to show you the CSV as well. I hope I don't forget. But this volumetric locking investigation. So this is basically um, when we say that the Poisson's ratio is equal to 5, what we're basically saying is that e to the x plus e to the y plus e to the z, but doesn't matter because it's 2d, equal to 0. What we're saying that e to the x equals to minus e to the y. That is the incompressibility equation, right? Condition. So we're basically saying that if it's incompressible, then and it's volumetrically the same, volume remains constant, whatever strain you apply here must be equal and opposite, like must have the opposite sign in y. But look at the nodal, look at the constraints over here, right? If I am applying a load over here, this will result in some strain, and this strain must match the strain in this direction negatively. But these are fixed, these nodes are fixed. So essentially, this condition cannot work. So it becomes really, 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 really stiff. This is what happens physically. Mathematically, mathematically, K equals E over 3 over 1 minus 2 Poisson's ratio. This is the bulk modulus, right? How the thing bulk. So bulk modulus, like it's slightly different from um, bulk modulus is the quantity that you want to look at rather than the elastic constant here, modulus of elasticity. Um, but essentially, at when v approaches zero point 0.5, this approaches this goes to 0, which means that bulk modulus goes to infinity. And that makes the thing mathematically approach infinity and asymptotically. And that's what we see. So essentially, the plots, what the plots are depicting, they're depicting this situation. They're depicting this situation, this singularity kind of approaching in the FEA versus exact solution. Um, yeah, stiffness matrix condition number versus Poisson's ratio. So it goes to like infinity right here. And so you know, when the thing is infinitely stiff, then with increasing Poisson's ratio, the dip deflection that you're going to experience is going to be lower and lower, lower and lower and lower until it's going to be zero. There's going to be none, and you're going to do approach that asymptotically. That concludes the basic functional explanation. Um, I don't know if I did a better job in this one versus the seven other videos that I made. They're all tend to be 20 minutes long. I don't know why. Um, I feel like this is better. I'm gonna post this and try and make a second one. I just want to show you one more thing that I was supposed to show you, which is that my CSV output is working. So 231 notes given my current slider settings. If I go to download CSV, it was 231 notes. They start from zero. They start from zero, and so they go to 230 here. They should go to 230, right? So now I have 231 notes, and then x equal to zero. So these are the sort of undeformed state, and this is the deformed state. And so we can potentially add another deformed mesh versus undeformed mesh, but we don't need to. It's not strictly necessary because we are contour plot captures it fairly well. Yeah, I think that's everything. Thank you so much for watching. I hope to answer all the questions and the rest of the questions in the Viva. But what I try to focus on is like the physics of the problem and the some things that we want to be careful of to get meaningful results. We don't like the ratio of the applied stress to what is it, elasticity. Why we don't get the peak hoop stress at the exact location. Um, well, that's how we approximate the hole versus what is material, how it decays as we move away from the hole, because the material initially, the no traction free boundary condition at the hole. Um, I don't think I actually talked about this. So the traction free boundary condition over here. Um, I'm gonna reduce this so it runs fast. Um, yeah, the traction free boundary condition. Um, what it does is it yes. So sigma to XX, yes. So there initially there is no stress buildup, uh, and the reason for that is there is no material, right? Um, and as we move away from it, we have more and more material over here to build stress onto, and so and then until we finally get here and we get a value of one, and that has to do with the traction free boundary condition over here. Basically, the hole has no material, and there's no loading situation inside. Um, yep, that's uh, that's my explanation. And you can see, with a unrefined mesh, it's not near the equator. It's actually 675 degrees actually. So yeah, that's everything. I'm gonna upload this. Sorry it took so long. I apologize for that.